Yeah, I'm Marius, and yeah, I will talk about this work of ours, which is part of a paper that already is on the live, and some of the stuff that I will talk about today is still in preparation, but should be out fairly soon. And the talk will be regarding the learnability of output distributions of local quantum circuits. So before I start, let me just thank all my co-authors, which are quite few, who worked hard, and yeah, everyone is to be thanked for the result. Okay, so the fundamental object of our study quantum circuit distributions, and just to set the stage, what we mean by that are distributions generated by preparing starting with the all-zero state, applying some quantum circuit, and measuring. And of course, we know that the probability of obtaining some bit string x is given by the Born rule. And in particular, we are interested in local quantum circuits, and this we refer to like geometric locality in the sense that we actually say that all the gates are nearest neighbor gates, which reflects, most many of the current architectures out there. So the problem that we studied in this work is regarding given data, given samples from such a distribution, whether one can construct a learning algorithm that can output some kind of model for that corresponding distribution. So for those of you who are familiar with probabilistic modeling, this might sound familiar. Here you might have some data, maybe these are like pictures of people or something, for which you assume some underlying distribution, which is maybe very complex, and your learning algorithms, the task of it is to, like output a model for that unknown distribution so that maybe you can, generate new pictures or understand the probability density function behind it. But yeah, I will go into more details about what I mean by a model in this sense here. So exactly, we have like two kind of different models that one could wish to output for these. So actually, is it possible to like shift this a bit? Because the left-hand side is like cut off, but okay, anyway. So yeah, like there are two types of models that we could consider. And the one on the left-hand side, it's what we call density modeling. In this case, what you want is to output some model for the probability density function so that when you're given new points, you might be able to predict the probability of those. And on the right-hand side, we have what's called generative modeling, where you're given samples, and you want to construct an algorithm such that you can generate new samples on your own. So for example, maybe you have pictures of faces, and then you want to output a picture of a new face. And in particular, in this like second, in this generative modeling sense, there are many different ansatz in classical machine learning. For example, generative adversarial networks, which perform this task. But in the quantum machine learning literature, there's the idea of so-called Born machines, which are parametrized quantum circuits, which are a model class with which people are trying to solve problems of this kind. And really, the kind of motivation for our work is very practical, because I mean, it's trying to like set up a research program of basically understanding the potential of these Born machines for generative modeling purposes. And we know from prior work that these models are fairly expressive. And clearly, because of how it's structured, that you like have this quantum circuit, this parameterized quantum circuit, you also need a quantum computer to run them. So there's been the hope that maybe there's some quantum advantage in this task. In fact, you can actually prove a quantum advantage if you consider a very contrived concept. But okay, we are wondering whether maybe you could even get a quantum advantage from something much more natural than that. Okay, so having given this kind of machine learning perspective, I mean, one could also have motivated the whole work from a much more, theoretical computer science direction, but I guess it's nice to give like a more practical perspective. Now I want to like formalize things a little bit, and for this in order to be able to like characterize such algorithms, we consider the distribution learning framework, in which one considers, first of all, a concept class, which is a subset of all distributions over 1 to the 1 and 1 or 0, 1 to the n. And the learner is given some unknown distribution within this concept class and is asked to output a model, as I just said, a generative or a density model for this unknown distribution. In particular, like, for example, in this example that I gave with the facial pictures, one is not like in this formal framework. If the concept class are, let's say, pictures of people, then it's like you're not going to get any other pictures, or you're not also asked to perform the task of outputting pictures of landscapes or so. Like you have to perform well on this kind of subset of distributions. Okay, so just to point out, the way that the learner interacts with the samples is purely classical, because that's the way we set it up, because we think this is like the most natural way to consider access to data right now. But we don't assume anything about the learning algorithm itself, or in fact about the model. These can in any case be classical or quantum, or both. So this is fairly general. And furthermore, we also don't want to be too unrealistic. We assume we allow some slack to the learner, and so we allow him to approximate the distribution and not output, a model for exactly the right distribution. And this approximation is in total variation distance, essentially. And when I will be talking later on about the complexity of such learners, I will primarily be concerned with time complexity. And when I say hard, we mean super polynomial, of course, but one can also study these problems from a purely sampling complexity perspective, which is also super interesting, but here we mainly focused on time complexity. Okay, so just to give a small kind of example of what, how one treats how this looks, we consider the learning of product distributions over 0, 1 to the n. Here the concept class now are product distributions, and now our learner is given bit strings where each bit is distributed according to P1 to Pn. And essentially the task here boils down to learning biases of n coins. And this can be done efficiently with polynomially many samples and time. So we would say in this case that the concept class of product distributions can be efficiently learned with respect to generative modeling or density modeling. Now turning to the concept class that we consider, namely the distributions generated by quantum circuits, we can see that there are like basically two parameters that play a role in the description of the concept class, namely which gate sets the local gates are from and the depth of the circuit. And yeah, there are two extreme cases that one can consider, namely the case where you have just a single layer, and essentially here the problem or the concept class is the class of product distributions again, and as we just saw, this is easy to learn. And the extreme case where the depth goes to infinity, and here you can actually construct all distributions, and now in this regime it's known that this is a hard task. And basically we are kind of asking ourselves, okay, can we paint a more kind of fine-grained picture of this complexity landscape by basically looking at these two parameters. So our results will be concerned on the dependence on the gate sets and on the dependence on the depth of the circuit. So I'll start with considering Clifford circuits. Here basically every local gate is drawn from the 2-qubit Clifford group. And we know that such circuits are efficiently simulatable. And basically what we are asking ourselves is, is there some kind of correspondence between the complexity of learning and the complexity of simulating such circuits? And as we can see, there's been also some prior related work on this, where people have considered slightly different learning settings, but have shown that actually for Cliffords there is this kind of correspondence. And for example, learning stabilizer states is efficient, and when you add T-gates, the complexity grows exponentially in the number of T-gates, which is also in correspondence to the results we know for simulating such circuits. And indeed, in our distribution learning setting, we find something similar, and we find that both density and generative modeling is easy with purely Clifford circuits. Just to give the rough idea of how one and when I mean easy, it means we provide a learning algorithm which runs in polynomial time. The idea is that here the output distributions are very structured. Basically, they are uniform distributions over some affine subspaces, and all one needs is to basically reconstruct the affine subspace in order to obtain a model. Interestingly, though, we find that adding a single T-gate, unlike the setting that these other people have seen, where they saw like this exponential growth in the complexity, we actually see that adding just a single T-gate leads to like a huge gap in the complexity. And namely, we find that density modeling becomes hard in this case, and we actually don't know the exact situation regarding generative modeling, but yeah, density modeling becomes hard. So we see this kind of imbalance between learning and simulation. So there was this kind of, I don't know if one can call it folklore belief, but like some people had this idea that, okay, if you can simulate it, then you should be able to learn it. And we see that this is not the case always. And again, the idea here, just very rough, of why this becomes hard is that once you add a single T-gate, essentially the distribution that you get is a mixture over uniform distributions of affine subspaces again. And in this, you can embed the problem of learning parities with noise. And this is known to be hard, or conjectured to be hard. OK, so but having shown this, and we've seen that it's hard to learn density models, but for Clifford, for T-gate enriched Clifford circuits, now we want to move away from this restriction on the gate set, and we instead want to consider generic quantum circuits, and we want to study the complexity and how it scales with the depth. And in particular, we also want to address the question of, generative modeling, for which we so far only have, we don't have a result yet, right? OK, and the first result that we find here is that learning generic or general circuits, whereby I mean that the local gates are drawn from some universal gate set of depth n to the omega 1, is hard in both the generative and density modeling sense. And I'm not going to go into the proof details here, but the idea is that, again, you can embed a hard problem. In this case, you can embed some pseudo-random function into the output distribution. And by that, if one could learn, then one could distinguish this pseudo-random function from a genuinely random function, which this you shouldn't be able to do. And so you get a contradiction. OK, but so this was for this particular depth. So this still leaves open the question of what happens if we consider shallower circuits. Maybe they are learnable. Maybe the hardness only comes in because you consider relatively deep circuits. And to be fair, at this point, we have no handle on when we consider this most general setting of what happens at this, more shallow circuits. So what do? We do what one usually does. We simplify the problem a little bit, and we just restrict our attention to what we call generic algorithms. These are algorithms that, unlike the, say, Clifford algorithm that I just sketched before, where you kind of learn the subspace from the samples, these algorithms, we say they should use coarse-grained statistics from the data rather than exploiting algebraic structure. And the idea is that if an algorithm is generic in the sense that it's not supposed to work only for a particular class of distributions, then it can't be relying on such specific algebraic structure. This kind of idea can be formalized in what's called the statistical query model. So on the left-hand side, this is the model that we considered all along. Basically, you have an unknown distribution, you get samples, and you try to learn from those. In the statistical query model, which is a strictly weaker model, the interaction is not direct with, you can look at it in this way, that basically the learner doesn't get samples, but rather he can query any function and is given back approximately the expectation value of that function under the distribution. Or you can basically also, this is kind of what I sketched here, you have this SQ oracle, which gives you the expectation values. But you can also think about one, essentially, and basically just consider the learner as restricted, so that they use the samples to construct to compute expectation values of functions. And okay, maybe you think, okay, why did they look at this contrived kind of setting? And so first of all, most algorithms that we came across are actually of this type. And as I tried to sketch or like motivate a bit, we say that these can be considered as generic in a sense. And in general, we kind of, one can kind of see results in this statistical query model setting, usually as evidence also for the generic setting. And the nice thing about going into this SQ model is that here you have some standardized techniques which allow us to prove lower bounds via so-called statistical dimensions, but I'm not going to go into this here. Okay, so this brings me to the second theorem, and which basically is like what we said before, like but for shallower circuits, right? Like as you can see also from the picture, here we show hardness of learning these general circuits, both in the generative and density modeling sense, but now for omega log n deep circuits. Okay, I think, so I lost track a bit with the time, but maybe it's, yeah. So anyway, this is the outlook for now, because, okay, we've seen that we could show hardness in the most general case for these rather deep circuits. We could push it down by restricting the axis or the algorithm, the algorithms that we allow to logarithmic depth. And now it's open what happens at very shallow circuits for essentially constant depth circuits. Are these easy? Are these hard? We don't know. It would be nice to find out. Another question that we have and we are working on right now is we try to bring this closer to heuristics in a way by considering average case results, because obviously these are everything that I talked so far was in the worst case. And another point is that of exploring other sub-universal circuits, maybe match gates, etc. Maybe you've seen that there was a paper by Scott Aronson last year, which was retracted in the end regarding free fermions. Yeah, this kind of questions. And this brings me to the end of my talk. This was maybe a bit shorter, but I think no one complains about a short